Welcome students once again into the class of topology, and as you know that in the previous lecture we were doing the chapter of filters, so I am continuing from where I have left in the previous lecture. So let us move on to the next definitions and theorems and the rest of the concepts of filters. So the definition from where I am going to start is supremum and infimum of a family of filters. Let M be a family of filters on a non-empty set X. So we are having a non-empty set X, then we are having several filters on X and their family is M. Now, supremum of M, what is infimum of M? We will be talking about that one now. First, I am going to tell you orally what is supremum of a family. Supremum means a filter which is finer than every member of this filter. A filter of M which is finer than every other filter of M is said to be supremum of M. Mathematically, a filter F is said to be supremum of M if, number one, there are two conditions. Number one, F is finer than F dash for every F dash belonging to M. That means F is finer than every filter in the family M. Second condition, if F double dash is also a filter finer than every filter of M, then F is coarser than F double dash. That means it is finer than every other filter, but is coarser than every other such filter, which is finer than all the filters of M. So this is the definition of supremum, and similarly we can define infimum of a family of filters. So once again, let M be a family of filters on a non-empty set X. A filter F is said to be infimum. This time we are going to define infimum is said to be infimum of M if and only if now you know what to do. Just to change finer by coarser and coarser by finer. So F is now coarser than F dash for every F dash belonging to M, and if F double dash is also a filter which is coarser than every filter of M, then F is reversibly, it is now finer than F double dash. So what we have to do from when we define infimum from supremum, just replace by finer by coarser and coarser by finer. You will get the definition of infimum of a family of filters. Now we move on to some examples of supremum of a family of filters and infimum of a family of filters. Let us see what these examples are. For that, we will have to define a set X, some filters on that, and then a family, and then we will take supremum and infimum. So let X be the set ABC. Let us have filter F1 as containing of A, B and X, filter F2 as BC and X, filter F3 as AC and X, and let F4 be a filter containing only X. That means indiscrete filter we are talking about. Now consider this family M containing all these filters F1, F2, F3 and F4. Now look that, is there any filter in this family which is finer than each of these filters? That means which contains all these filters? No, there is no such filter. So that means this M has no supremum. But yes, it has an infimum. This filter is infimum because it is a filter in the family F and it is coarser than every other filter, or you can say every filter of the family M. So here you can have an example of supremum of a family and infimum of a family of filters on a non-empty set X. Now we'll define another important definition, that is filter base. Filter base. So what is filter base? Once again we start with a non-empty set. Let X be a non-empty set. Let X be a non-empty set. Let B be a subset of power set of X. That means B is collection of some subsets of X. Then B is said to be a filter base, is said to be filter base on X if two conditions are there. Number one, phi should not be there in B. Phi should not be there in B. Secondly, if B1 and B2, if B1 and B2 are two members of B, then there exists another member B in the family such that B is contained in B1 intersection B2. If these two conditions are satisfied, then B is called a filter base on X. So now there is a question which normally arose in the mind. If there is a filter base, then there should be a filter generated by this filter base. And yes, there is a filter generated by filter base. And what that filter is, let F be the collection of all those subsets of X, such that F contains B for some B belonging to the filter base. Then this collection becomes a filter, and that we will prove later on that this is a filter. And this filter is called filter generated by B. Now it may happen that there are two different filter bases, but they generate the same filter. There is a possibility of this type, and if two different filter bases generate the same filter, then such filter bases are called equivalent filter bases. So just now we have defined equivalent filter bases. Once again, I repeat the definition of equivalent filter bases. Two filter bases, let these be B1 and B2. Two filter bases B1 and B2 are said to be equivalent filter bases if they generate the same filter. So this is the definition of equivalent filter bases. Now, based on these things, one thing is very much clear, that every filter is a filter base, and we will prove that. There is a theorem, very trivial, that every filter is a filter base. And let us see how to prove this. The proof is once again very easy. So what we have to do, we will take a filter. First of all, we will take a non-empty set X, then we will take a filter on X, and we will show that that filter is also a filter. base. So let X be a non-empty set and let F be a filter on X. We will show that F is also a filter based on X. And for that we will have to prove two conditions. Number one, that phi does not belong to F, and secondly, if F1 and F2 are two members of F, then there exists a member F of filter F such that F is contained in intersection of F1 and F2. So let us see what the first condition says. First condition says that phi does not belong to F. That is required for the filter base. And yes, it is true because F is a filter. And we know that phi does not belong to a filter. So definitely first condition of the filter base is clear. Secondly, let F1, F2 be two members of F. Now what we are to prove? We are to prove that there exists another member of the filter F which is contained in the intersection of these two. Now F is a filter. By the definition of filter, second condition, if F1 and F2 are, third condition, if F1 and F2 are in F, then F1 intersection F2 also belongs to F. And take it as F. Rename it as F. Denote F as F1 intersection F2. So we can say there exists F in F such that F is contained in F1 intersection F2, because F is nothing other but it is F1 intersection F2. So the condition is trivial. So both the conditions are satisfied for F to be a filter based on X. So that means F is a filter based on X, and this proves that every filter is a filter base on the set X. Let us have one more theorem in this video. And first write down the statement of the theorem and then we will prove it. Statement says, let B be a non-empty family of non-empty sets on non-empty sets, or you can say non-empty subsets of X. Non-empty subsets of X, because X must be there. If X is there, only then we can talk about filter and filter base and so on. So we have taken B to be a non-empty family of non-empty subsets of X. Then this B is a filter base on X if and only if the family of subsets of X that contain a member of B is a filter on X. So this is a theorem which we are going to prove now. So let us see the proof, how to prove it. So first we suppose that F is filter. What F is? We are given F is collection of those subsets of X such that F contains B for some B belonging to the collection B. We are given this. Suppose F is a filter. So that means this we have taken, that this is a filter on X. And what we have to show that? We have to show that B is a filter base. F we have taken to be a filter, and we will show that B is a filter base. And B is a filter base if it satisfies two conditions. And what two conditions are? Number one, phi does not belong to B. And if you look closely to the statement of the theorem, it is given in the statement that B is a non-empty family of non-empty subsets. So B contains only non-empty subsets. That means phi is not there in B. So first condition is very much given in the statement. And now we will move on to the second condition. Let B1 and B2 be two members of B. So what we are to do that? We are to show that there is a member of B which is contained in B1 intersection B2. Okay. Since F is given to be a filter, and every B1, every B2 is contained in some member of the filter, so there will be two members F1 and F2 containing B1 and B2. So, or you can say that since B is contained in F, or you can say like this, because B is contained in B, so B will also be there in F. So that means every member of B is a member of F, or you can say that B is a subset of F. So that means B1 and B2 are members of F also. But what about F? F is a filter. And since F is a filter, by the definition of filter, B1 intersection B2 also belongs to F. B1 and B2 are there in F, and F is a filter, so B1 intersection B2 is also there in F. But by the definition of F, it contains only those sets which contain some member of B. That means this B1 intersection B2 must also contain a member of B. So that means there exists B in the family B such that this B is contained in B1 intersection B2 by the definition of F, and that is nothing but the second condition which makes the collection B a filter base. So one side we have proved that if F is a filter, then B is a filter base. Now let us prove the converse part. Conversely, suppose that B is a filter base. Conversely, let B be a filter base on X, and we are to show that, to prove F is a filter. We are to show that F is a filter, and for that we are to prove the three conditions for F to be a filter. The first one is that phi does not belong to F. And that is very much true, because B contains only non-empty sets and F contains supersets of the members of B. So definitely phi will not be there in F. So first condition is okay. Secondly, let F be a member of F, and let H be a superset of F. We have to show that H also belongs to F. Now F belongs to B. F belongs to F. And every member of F contains a member of B. So therefore, there exists B in B such that B is contained in F, but F is contained in H. So that means H contains B. And every subset of X that contains B is a member of F. So this means H belongs to F. So second condition is also satisfied. Now move on to the third one. Let F and H be the members of F. By the definition of F, there will be some B1, there will be some B2 contained in F and H respectively. There exists B1, there exists B2 in the family B such that F contains B1, H contains B2. And that means intersection of F and H contains intersection of B1 and B2. So F intersection H contains B1 intersection B2. But what is B? B is given to be a filter base. And by the second condition of filter base, if B1 and B2 are in the filter base, then B1 intersection B2 must contain a member of B. So that means therefore there exists B in B such that B is contained in B1 intersection B2, but B1 intersection B2 is contained in F intersection H. This means B is contained in F intersection H. That means this F intersection H contains a member of B. And whatever the subset of X contains a member of B is a member of F. So this F intersection H belongs to F, and it satisfies the third condition for F to be a filter. So that means if B is a filter base, then F is a filter. So I'm going to stop this video here. In the next video we will have more theorems, more definitions, more concepts on filter. Till then, thank you. Thank you once again.